The second side of the worksheet from section 6.4 goes back to 6.3 as well, because we're looking at exponential and logarithmic functions as their graphs, and really the idea here is just to use the fact that we know roughly what these things look like to be able to plot a few points, do a little bit of analysis, and draw a decent picture. So, for example, the function f of x equals 2 minus 2 to the minus x, it's got a lot of minuses in it. So like one of the first things we can do that's easy is calculate is find the intercept. So we know the y-intercept happens when x is 0. So we do this calculation. 2 minus 2 to the 0 is 2 minus 1, which is 1. So the y-intercept of this curve is at 0, 1. And then to find the x-intercept, we set the formula equal to 0 and solve for x. And so in this case, that's not hard because we have, I could just add the exponential thing to both sides. So just rewrite it as 2 to the 1 equals 2 to the minus x by subtracting 2 to the minus x from both sides. And then this is one of those special exponential equations where both sides are powers of the same base, and so therefore negative x has to be 1, so x must be negative 1. So that's my x-intercept. Now, one thing I know about exponentials is that they should have a horizontal asymptote, and they should fly off the screen in the other direction. And so if I just plot 2 more points, I should be able to tell what's going on. And I'll plot them far away from the center, so I'll figure out what f of 4 is, and I'll figure out what f of negative 4 is. And this ought to tell me more or less what's going on. So f of 4 is 2 minus 2 to the negative 4, which if you put it in your calculator is 1.9375. So 1.94-ish. So that's out here. So out at 4, we're almost to 2. And if you look at the structure of this, you can see that this is just 2 minus something, and this something is going to get closer and closer to 0. So it makes sense that this guy is getting closer and closer to 2. So that tells us our horizontal asymptote is 2, which means it should be flying off the screen in the other direction. So let's try it. 2 minus 2 to the minus 4. So that's 2 minus 2 to the 4th, which is negative 14, and that definitely doesn't fit on my screen anywhere. So so my graph is basically has an asymptote out to the right at y equals 2 and is flying down very quickly. So from that I can tell my domain is minus infinity to infinity. We don't expect to have problems from raising things to a power. That doesn't cause errors generally, or it doesn't cause errors by itself. And then the range, we can see from our picture that it should be minus infinity to 2, not including 2. Remember, the range is the extent of the y-coordinates, and we always expect with an exponential function that the range horizontal asymptote as a barrier. So the answer for the horizontal asymptote being y equals 2 is the asymptote. Is going to correspond to the range. The asymptote is a barrier on the horizontal asymptote is a barrier on the range. So that's the kind of game we can play, and it's not hard to do that with the other problems here. The log function looks a little different, so make sure you do some of logs and some exponentials. So right off the bat, for example, g of 0 should say error, because remember, the number that goes into the parentheses here for a log function, no matter what base it is, has to be positive. And so, in fact, for the log function, it makes sense maybe not to necessarily start with the intercepts, but start with the domain, because the domain is very obvious from what goes into the parentheses here. So the stuff in parentheses, the x, has to be positive. So the domain here is all positive x's, which as an interval we would write as 0 to infinity. And so it's always going to be something like that, but we do it by taking what's in parentheses and asking ourselves, when is that positive? And then similarly, the range is generally minus infinity to infinity, as long as we don't do anything too crazy to the logs, but that's what we expect to see. Again, the asymptote for the log is vertical, and it should be a barrier on the domain. So just like the exponential had a horizontal asymptote that was a barrier on the range, the asymptote for a log function is going to be a barrier on the domain. So once you decide what the domain is, then then your asymptote is going to be exactly at the edge of that. Another way to think about it is that the asymptote happens when the number that goes in those parentheses is 0. So whatever makes that 0, that's going to be your asymptote for the log function. Notice that at the one down here, there's a more complicated expression in the parentheses, and so here the vertical asymptote is going to be -2, x equals -2, because that's -2, because that's the value of x that makes the stuff in the parentheses 0, and then the domain down here is going to be from -2 to infinity, because we want to make sure that whatever x we've used, the stuff in the parentheses is positive. So the x being positive is not really the issue here. The x could be -1, and that's totally fine. But the stuff in the parentheses has to be positive. And so that only happens when x is bigger than -2, which is this domain. So notice how the asymptote and the domain go together for logs, and the asymptote, the asymptote, which is y equals 2, and the range go together for exponentials. And this is because of their basic shape. We saw there's no y-intercept then for g of x. And so we might then ask, what about the x-intercept? And the x-intercept, remember, happens when the formula for our function, this formula, is equal to 0, because that makes the y-coordinate equal to 0. And so we can do this using the same method we did on the other side of the page. We isolate the the log expression that has the x in it. So dividing by both sides by 5 would give me that. And then if I rewrite this using exponential form, it would be e to the 0 equals x. Right? This is a log base e, and so its inverse is going to be exponential base e, but this output becomes the input, and the input becomes the output. And so don't forget that raising something to a 0 power is 1. So there's an x-intercept at 1, 0. There's a vertical asymptote at x equals 0. And my expectation is that that my x is going to get close to this thing. And this is why I really only have to know whether it's going up or going down. And so if you really plot any other point, so for example, plot g of 1, g of 1 will be e, so g of 1 was 0, sorry. So I plot g of 2. And to do that, you'll need to use your calculator, but because the base here is just base e ln, then you're just calculating 5 natural log of 2. And it looks like 5 times the natural log of 2 is about 3.5. And keep in mind, I don't have to read this very accurately because my graph is pretty coarse. So about 3.5 is good enough, and then I can plot that about 2, and 3.5 is about there. And so the basic shape of log functions is that they hug the asymptote in one direction and then are increasing the other way. Don't forget that the log is not horizontal asymptote. It does not grow very fast this direction, but it does not ever, there's no barrier to it. It'll keep going up forever. So that's what the log function looks like. And it really, if you remember what one of these looked like, the other one is just the other way around. Notice that this hugs a horizontal asymptote and then flies away from it in the other direction. This hugs a vertical asymptote and flies away from it in the other direction. And that's always going to be true. Exponentials always will look like that, and logs will always look like that. All right, so let's let me do this. I think we have a little more time. So let me just do a little bit more of these guys. I'll finish with D since I already started it. So at this point, just plotting some points would be the way to go. So, for example, P of 0 is log base 3 of 2. And don't forget, change of base rule. We can say that's ln2 over ln3 to find out what number that is, because in order to plot it, I'm going to need to know the actual numerical value. And it looks like that's about 0.63, so I'll call it 0.6, so a little more than a half. So when x is 0, y is 0.6, so about there. So that's my y-intercept. And my x-intercept happens, again, when the formula that I have, or the formula is a formula for y-coordinates. So it happens when that is equal to 0. And so to figure out when that happens, I just convert that to exponential form. And so that means that it's equivalent to the equation 3 to the 0 equals x plus 2. But since 3 to the 0 is 1, that means that x is negative 1. So when x equals negative 1, we have we have our x-intercept. So my asymptote is here at negative 2. I've plotted a couple of points, and so I can get a sense that this is going like that and hugging the asymptote on the other side. Because it's log base 3, it's pretty easy to plot a few other points, but if you want to get it to look better than that. But really, since we know the basic shape, the idea is just to plot the significant points, which are the intercepts, have the asymptote on there, and then draw the sketch so it shows that you know which way the graph is going and what its shape is. Okay, so real quick, this last one. It looks different because it's got an e in it, but that just means we have to use our calculator more. So the y-intercept happens when x is 0, so that's 3 times e to the 0 minus 4. And again, e to the 0 is 1, so that's 3 minus 4 is negative 1. So here's the y-intercept. The x-intercept happens when the formula is equal to 0, and so I should rewrite that in logarithmic form. If I get the e to the x by itself, this equation will say e to the x equals 4/3. So take a second and do that. Move the 4, divide by 3. It'll say e to the x equals 4/3, which means that x is natural log of 4/3, which is about 0.3, looks like. And so that's about, yeah. So that's somewhere in here. So that's my x-intercept. Don't forget that we expect this to look exponential, so it's going to look like this first graph. It's going to have we expect it to have a horizontal asymptote that hugs in one direction and goes away from it the other direction. So let's see if we can see where that happens. Again, the easy thing to do, if you don't want to think about it, is plug in some extreme values. So let's say negative 4 and 4. Those are the biggest numbers that are on my graph paper. So we could see what points we should plot for these two guys. So h of 4 is 3 times e to the 4th minus 4. And if you do that, it's approximately big. It's a big number. It goes off the screen. And h of negative 4 is 3 times e to the minus 4 minus 4, which is approximately negative 3.9. So that's down here. And once again, if you think about it, this is the part that's making the answer small. And if this becomes negative 10 up here, this is really small. So you're really close to 0. So this is the guy that's getting close to 0 that's causing this to happen. And so it makes sense that this expression is getting closer and closer to 3 times something really close to 0 minus 4, which means it looks like our asymptote is at negative 4. And so now that I know a couple of points and I know where my asymptote is, I know the basic shape of this exponential graph.